I'm Matt Butcher. This is Chris Madison. Chris is our head of solution sales, also highly technical individual. He's going to be showing a really exciting OpenShift plus WebAssembly thing coming up here. I'm going to give you a little bit of the introduction. I was the creator of Helm, worked on a whole bunch of Kubernetes stuff very early in the community. The startup that we were involved with ended up getting bought by Microsoft, and I spent a number of years at Microsoft. And one of the things that we devoted a lot of time to trying to solve there was compute related. How do we squeeze more compute efficiency out of the resources that we already have? So today we're going to talk about WebAssembly, because WebAssembly is what we found is sort of the solution to this problem. But I'm going to start by talking about what WebAssembly is and kind of why it got us going, because I know some of you are familiar with WebAssembly and going, wait a minute, isn't that a thing that goes in the web browser? Because yes, in fact, the original idea with WebAssembly was, going back to the early days of like the Netscape browser, maybe we can make a runtime that is platform neutral, that is architectural agnostic, that runs inside the web browser, and we can compile different languages to that bytecode format and run it inside the web browser. Now, why is this of interest in a web browser? Well, because we have littered the world with lots of different kinds of source code. We don't want to re-implement every C library in JavaScript. Sometimes we care about performance. And so these were all compelling reasons to build an engine inside of the web browser that would give you the ability to run binaries that were written in whose source language was something other than JavaScript. We got looking at this from the compute angle, right? So we're working on large Kubernetes clusters, huge amounts of compute power at Microsoft, at Azure, and going, we want something that has a very particular runtime profile that we can't figure out how to get elsewhere. It needs to have security, needs to be cross-architecture, cross-platform, needs to be exceedingly fast, and it should be able to support any language. So we started looking for candidates out there, technologies that could already do this, and we landed on WebAssembly. So that's sort of WebAssembly in a nutshell. Now I'm going to spend some time telling you what we were trying to do, and now what we as Fermyon have done. So I think many of us come from kind of the pre-cloud infrastructure world, where essentially we were looking at a one-to-one relationship between the server that we had physically located somewhere in a data center and the operating system that sat on top of it. In fact, I had gotten so engaged in this model, just thinking, okay, there's always one, the relationship is always one-to-one, that the first time I saw something divert away from that core assumption, I found it very jarring. So I ran into the concept of virtual machines and thought, oh, this is weird, right? Suddenly you're telling me I can have one piece of hardware and it can run not one, but some number of copies of the operating system. And I started looking at this, and it intrigued me. At the time I was doing content management system development. I was working in Drupal, and I hired on at HP to work on this HP Cloud project. And the HP Cloud project was based on OpenStack. And I started writing the documentation for some of this as part of my responsibility working on the content management system, and went, whoa, wait a minute. This is a game-changing technology. If I can suddenly start using this hypervisor to run multiple copies of the operating system, then we're going to change the way we do infrastructure management. So I asked to be transferred out of the CMS team and into the OpenStack team, and that was sort of the point of no return for me when I really got into cloud technologies. So there's the virtual machine. It's a big, giant thing. It's an entire operating system from the kernel and the drivers all the way up through the entire system libraries, the OS utilities and all of that, all the way up to the application I want to run. It is an absolutely fundamental piece of the cloud, and we will never be able to get away from it, right? But it's big, and developers do not like developing these things. I, as a developer, found them very frustrating to try and build machine images, and then I'd hand them over to the operations team, and they'd be like, oh, well, you need to update this, you need to change that, did security audits say this? And when containers came along a little bit later, I was the developer out there who was going, oh, this is it. This is so much better than a virtual machine, right? Instead of worrying about the kernels and drivers all the way up the stack, I'm just packaging up one little thin wedge of an operating system, the file system pieces that I care about, the libraries that I care about, and my application, and that's the only thing that lives in this nice little wedge-shaped cutout of an operating system. So containers, they had a lot of virtues compared to virtual machines. Virtual machine takes minutes to start up. Container takes up seconds, right? Virtual machine images were very difficult to build. Containers, much easier to build. But then at Microsoft, as we're starting to look at this compute power problem, we're going, there are some architectural issues with containers that we cannot figure out how to solve. We wanted a startup speed that went from seconds to under a millisecond. Why? Well, because serverless functions had started to gain traction as a way that developers wanted to build things. Now, AWS Lambda, it takes about 200 to 500 milliseconds to cold start a function. Google's search algorithm starts dinging you if you take more than 100 milliseconds before delivering your first byte to the user. So we looked at this and went, so there's literally no way you can write a high-performing website on Lambda, right? Google will penalize you, and they penalize you for a good reason, because users, when they watch a web page load, their attention begins to wane at around 100 milliseconds. That's how quickly we as humans get distracted by little notifications and things that are popping up elsewhere. So this was a problem we really cared about solving. But we needed those same technologies, those same features of the cloud, right? Security by default. We really wanted cross-platform and cross-architecture because we really wanted the developer to say, I build it once and I can deploy it, and we don't ever have to tell you what the infrastructure is running behind it, right? This is how we all want things to work, right? The developer can use their preferred tools, deploy it to us, and we don't have to go back and say, so we switched from Intel to ARM now, and we need you to go pick a new set of system libraries and rebuild this image. And they say, oh, now I have to cross-compile and things like that, right? They develop on Windows and Intel. We run on Linux and ARM, and there's no difference, right? The developer never has to know that we just switched platforms on them. That's the kind of reasoning that led us to WebAssembly. So with WebAssembly then, we're not packaging up really any of the operating system. We're packaging up just the binary and just its source files. So that's sort of the brief story of why we got into WebAssembly and this kind of way that we view the world. There are containers, the heavyweight class. Virtual machines, the heavyweight class. Containers, the middleweight class. And now WebAssembly, this lightweight class that is good for anything that has to really be able to start up really quickly, process a workload, and then shut down really quickly. In order to sort of realize this vision of the world, we built a couple of things. One of them is Spin, and the other one is Fermyon Cloud. We'll talk mainly about Spin and then running Spin in OpenShift today. But Spin is a framework for building these kinds of applications. You can essentially think of it as a serverless platform that developers can target, compiles your binary to WebAssembly, and then you can run it in any kind of Spin-compatible runtime. Spin's all open source. It has a couple of really cool features. In addition to being a WebAssembly-based function as a service style of application platform, it also has built-in key value storage, SQL database, really good CLI that's very developer friendly, and then most recently we added AI inferencing. So a developer can literally write AI inferencing applications with just a function call. They don't have to connect to anything, they don't have to know any credentials, none of that. The reason why we built a system like that is because once more it shows off this sort of platform agnosticism. Not only do we care now about memory and CPU utilization, we also care a lot about GPU utilization.
Sure. So when we do architectures on containers, right, like inherently, when we're doing horizontal auto-scaling, we need to make sure that the resources are there in order to address the request that's coming in. Right? When we're talking about things taking seconds to load, right, that means that I need to be able to predict in advance where the curve is going, and when I've hit 80%, 90% utilization, whatever the threshold I'm hitting, I need to start deploying more resources. And I go, let's go put another pod, another replica out there somewhere. And inherently this results in over-provisioning. We provision before we need it, and then we keep it up even when we're not using all of it. And you kind of go pick what you want when you're doing any kind of scaling with this, but inherently we end up with a waste of resources because of this architecture. This is still much better than if I kept this thing on the entire time and I architected for my peak. But the whole purpose of the cloud is you should be able to buy services for when you're actually using it, right? And serverless is what's been trying to be that promise. The reality is, though, if you look at, like, say, like AWS with Firecracker or Azure Functions, like they're using virtual machines or containers under the hood, and they're doing the same thing. They have to go start up these things here, so they're not as efficiently utilizing the underlying infrastructure. That's really what the powers of WebAssembly gave us, is to really efficiently utilize the underlying infrastructure. And so you can see this here, right? Like this is the serverless promise. You just provision what you're actually using. And even with, so again, like with Lambda or something like that, you're going to pay for the time your request is running, not all the things they have to do to start it up. But really, you're paying for all of that anyways, because they have to make up for those costs somewhere. If you can find a solution, and this is what we built with WebAssembly, is something that more efficiently time slices the CPU, then you can really only pay for what you're using and allow us to maximize what's going on in that system. So next slide. And so this is, really this is what I like to see the magic of like why this happens, right? This is the, your application, the drivers, the kernel, all this. This may be a container, this may be a virtual machine, but you're looking at hundreds of megs in size in order to generally deploy even a simple application. Spin applications are often megabytes, like single-digit megabytes. You can even get them smaller than that. Sometimes you're up to the tens of megabytes, but we're an order of magnitude or two smaller. That's what allows it to be super fast. We do a couple other tricks that you can't really do otherwise. So one of the things we do with something called Wiser is we pre-initialize the function up to the point where it's about to take the first request. So for instance, if I was going to run a Python application locally, I've got to load the Python interpreter, load the code into that, and all of that takes hundreds of milliseconds or seconds in order to do, and then it starts executing. For us, we've actually pre-initialized it and stored that in memory at the point where it's ready to accept the request. And so we'll get a sub 1 millisecond faster than you would if you just ran the thing locally without putting it inside of Spin. And of course, this is part of that piece of being portable here too, right? As we're going to talk about, we talk about Fermi Cloud as one place to deploy stuff. We're going to go look at OpenShift and really any Kubernetes cluster as alternative. But people have been able to go put this in all sorts of things, in endpoints. And we even have a company that's evaluating putting this in a car, right? Like all of these places that you could potentially want to go run this on different architectures, but to be able to have that consistent developer experience and have that high performance. Because frankly, it's just really, really small, and that helps everything. So next slide. Fermi Cloud, we happen to use Nomad. I'm a former HashiCorp employee, so I'm a little biased towards that. It's very, very efficient, and what it does, super simple to use, but let's be real, Kubernetes is everywhere, right? Like we have Kubernetes, there's the HashiConf, there's not even a Nomad conf, just HashiConf by itself is nothing on KubeCon here. And so one of the things we want to do is make sure that we could meet people where they're at, right? If you already have an orchestration engine, right, and a lot of people already have Kubernetes, let's go make sure that we work there and we work efficiently and easily on that. So go to the next slide. So this is the older version, but that's fine. So there's a bunch of different steps we did with this. Step one, we did the kind of the virtual kubelet. This was crustlet, and it was basically just wrapping up what we're doing inside of a bigger container. We don't really see that as a success because it still had a lot of the size that we didn't really want to bring along. So we moved on to the next level, and in combination with Microsoft, what they were originally writing for AKS was a shim for containerd, which allowed Kubernetes, so once you install the shim, you install a custom runtime class for Spin, and now I can directly execute Spin workloads right inside of my cluster. And now we have this, so you can run a simple Helm chart that'll install a daemon set. Within 15 seconds, now you can go deploy Spin workloads to any Kubernetes cluster, be that AKS, EKS, on-premise, whatever you want. We can go deploy a Spin workload there. And we'll respect all of the same things you're used to here, of them saying like, here's the max memory, the max CPU, the stuff you're doing in Kubernetes. But instead of taking up the resource where I'm going to maybe I'm getting dozens of containers in production onto a node, right? We can put hundreds of these on a node in using the shim, because ultimately each of them just has a little HTTP listener, and that's the only thing that's there that's running up until you get some requests. And in theory, the request can go take up the entire system and then scale back down and make that system available for other applications to utilize. And this is kind of step one. We'll get to where we're going next. Right now we're working on, so there's an official AKS experimental. You can add it without using the Helm chart. There's in the Azure CLI, you can install it. We're going to have that similar coming to EKS here in the near future. Next step, we built a Spin plugin. So one of the things that the Containerd shim required is the Containerd only understands containers. And so we had to go wrap your application, even though it's really just the artifact, the WebAssembly, and the spin.toml, we had to wrap that inside of a Scratch container. Didn't really add anything to the size, but it added a couple steps. So we created this plugin in order to make this easier to go do those processes. We just scaffolded it out for you. You run a couple commands, and it's done. Super simple. You store it in your OCI repositories. That's a working methodology we have people using today, but it's like it could be cleaner, right? OCI supports, and we use OCI internally to store our artifacts without wrapping them inside of a container. There's really no reason to do that. So we've been working with the company Liquid Reply. They created something called Wasm in order to extend what we're doing around Kubernetes and really continue to improve this user experience so it works as seamlessly as possible. And so one of the things we're working on right now is native support in Containerd for OCI artifacts. So the same things that you would be able to store in OCI and then deploy to, say, Fermyon Cloud, you should be able to deploy that to any Kubernetes cluster. We also have a bunch of other things working on with them. So right now, we only support a HTTP, and something like 70% of all serverless functions are essentially HTTP triggered, but not all of them are. Some of them come off Redis, some of them come off messaging queues, so we're adding support for those. In Spin itself, in open source, supports these. We want to get that into Kubernetes. So again, you have a parity there of everything that works that you're used to using with Spin locally and with Fermyon Cloud should also work in Kubernetes. We want to have that ubiquity of where you can go deploy that everywhere. And again, we're even looking at deploying Spin outside of those areas as well. We've been working with F5 and Nginx on getting it into Nginx Unit. We have, there's another example of where we're deploying it to. Anyways, more and more places we're like, hey, everyone, go use it. Use this as an architecture so that people can move their applications around flexibly where they want to do it. Can you go back a slide?
Oh, yep.
Yeah. We're also improving the documentation on there, making sure that you can see, like, you can have more and more examples of how to do this successfully. And then finally, why we're here today. Now we go to the next slide.
Sorry, I spoiled it.
We got working on OpenShift. So we got using runc in traditional Kubernetes. We got crun on OpenShift, did not support the shim. And so we've, in combination with Liquid Reply and Red Hat, worked together in order to get Spin running through crun. So now you can deploy applications from Spin into your existing OpenShift cluster by simply adding the extra runtime class for this. And essentially what we're doing is we're modifying crun in order to call the static binary of Spin, which we're just loading into the executable path on your nodes. And then when you schedule an application or a deployment to your OpenShift cluster, it sees that the runtime class is crun Spin, and then it will actually go choose to use that runtime, the Spin binary, to deploy it. So I've got a couple demos here. We did it recorded, so they're not as cool as it's doing live. I can't channel my inner Kelsey Hightower, but we'll see kind of what's going on here. So first, this is just getting it set up. Essentially, we've already downloaded crun. Or download and get it installed. And sorry, not crun. This is a local OpenShift running. Obviously, using OpenShift, other deployments, something enterprise, you're already going to have that set up. And so we're just getting it installed here, and then we'll add that daemon set. That will actually deploy the binaries for the custom crun that supports this and for Spin into the cluster. And this it's a little accelerated. It definitely takes longer on my laptop than this video takes, but it'll take another few seconds here. And then next, we'll see actually deploying an application. If you're not familiar with Spin and our user experience, one of the big things that we really try to push from day one is making it as simple as possible, a consistent user experience across where you're deploying. And so part of that is ensure that I can run all of this stuff locally and then deploy it where I need to deploy it without any changes. And this includes where there. So here I'm adding that runtime class. And then next, I'm actually going to go deploy my application, which is just take an example off Deus Labs, is the Microsoft team that wrote the shim. And then ultimately, this will come up here. Oh, I had to actually hit the daemon set in here. And we'll see the pod will load in a moment. It's running. And then once I do this, I'll be able to hit it locally and see what's going on here. And so you can see it's very simple to go get this deployed. Cool. And curl localhost. Cool. So if you want to learn more about this, we invite you to go download Spin. Again, we're open source. Fermyon Cloud is free. The stuff for OpenShift is already on GitHub. It will soon be in our official documentation, but we're happy to point you towards that. Join our Discord community. Feel free to reach out to either of us and ask any questions or ask the people in the Discord community. We're happy to help if this is something of interest to you, that you would like to augment your existing OpenShift with super fast, super efficient serverless functions.
Thanks.
Thank you.